like 22 students now as advisees, so.
Okay, how do you schedule that?
Just come by.
Okay, like your
Yeah.
office hours?
No, just come by whenever. I'm usually done teaching at like 11:30, so just swing by, and the worst they'll say is come back in like 10 minutes or something like that. If you want to send an email, say, hey, I've got these times available, then we can set something up like that, but otherwise just, where else would I be, right?
Yeah, really. Oh dear. Oh, me and my friend are just gonna deer. And then we're don't laugh. And then like oh you like have to go with something. It's like it's all gonna be like stupid. So it's just sometimes the stupider is the funnier.
Making our way through Lewis structures, and we started to learn the basics on how to draw Lewis structures. We talked about one of the most important points, which is about formal charges and how we can use those. And the answer is we use them everywhere to check to make sure that we have the proper Lewis structure, and we're going to use them to figure out, or in some ways we're going to use them to figure out polarity, this kind of idea. And then the progression that we went with that was to resonance structures. And resonance structures are where we have these Lewis structures where we don't move any atoms around, right? The atoms are always in the same place. The only thing that we move around are the double bonds, or when we get really fancy, we move around triple bonds, okay? So we're moving around lone pairs and double bonds and this kind of thing, and that's what we end up calling a resonance structure, okay? And resonance structures are extremely important, but not yet. Right now, all their purpose is to annoy you guys and to, make me write an extra question on an exam or something like that. Okay? But I promise by the time you guys get to OChem, they'll be everywhere, right? So I wish it was kind of structured a little bit differently, but not everyone takes OChem, and so here we are anyway, right? So resonance structure is just kind of the idea that I want you guys to get out of it is that all resonance structures that you guys can draw exist simultaneously, right? So what we see is not the individual 3 resonance structures, but an average of those 3. The only thing we can do, right, is draw our snapshot, our picture that we take at each instance is what it is. But in reality, that double bond is simultaneously at all those different places here, right? And so that's kind of the I don't know if tricky is the word you want to use, but kind of the maybe the hard to understand type thing, right? It's very easy for us to understand that one thing exists at one place, right? That's how our universe works, right? But remember, when we're dealing at the quantum level here, right, things get a little bit more wonky, right? Classical physics kind of falls away, and we're left with quantum physics to explain how things work, right? So that's the other end of it. So we'll pick it up from there, but let's start with prayer then, and we'll continue on the march here, so to speak. But Lord, we just thank you. Lord, we just thank you for another day. We just thank you for another opportunity. Lord, we know that you've filled this day with wonderful things for us, Lord, and we just pray that you humble us in that understanding, Lord. Humble us in the way that we know that you've created this for us, and this is a blessing and a gift, Lord, and help us to be ever appreciative of that. Lord, just open our eyes just to understand the things that you've set before us, Lord, and just give us understanding and discernment just to where to spend our time and our effort and the things that you've put in our hearts, Lord. We just pray for the people around us, Lord. We pray that we can shine your light into their life in whatever way that you would have us do today, Lord. We just pray for that purpose, and we pray that you speak that purpose unto our hearts. We just ask this in your name. Amen. All right. So, resonance structures, we got it. There's carbonate. You can do it for nitrate. You can do it for nitrite. You can do it for sulfate. You can do it for phosphate. You can do it for ozone. See, which other ones am I missing here? I think I've kind of hit them all. Yeah, I feel like I'm missing one or two. Your chlorates and your bromates and iodates and all that kind of, right? Any of these polyatomic ions, they have, these highly symmetric looking structures where we got double bonds and we can kind of bounce around from place to place, right? So all of those would be very fair game for practice, right? In terms of, can we draw the resonance structures for nitrates or something like that, right? But spend a little bit of time kind of working through some of those and just understanding the consequences of them, right? And that's going to be useful for us. But if we take all these ideas and kind of summarize them down, that's kind of what this slide is here, right? Resonance structures must have the same connectivity, aka we're not going to be moving the atoms themselves, right? So only move. Still in OChem mode there. So only our electrons can change or can move. Now be careful, right? Because what we're talking about when we're saying the electrons can move, right? We're talking about pi bonds, which we'll define in just a little bit, right? Double bonds and triple bonds, and our lone pairs, okay? You can't move single bonds around, right? Single bonds and moving those around would break the connectivity between atoms. And you just don't do that in a resonance structure, okay? You do that in a reaction, but not in a resonance structure. Resonance structures must have the same number of electrons. One of the common mistakes is we go through and we add electrons, we just add a double bond, or let me just put another lone pair here because that makes life easier, right? That kind of thing. Right? Don't do that, right? Remember, every resonance structure has to be a valid Lewis structure. Not the best Lewis structure, right? Just a valid Lewis structure. And how do we go through and validate our Lewis structures? We got to count our electrons. We got to make sure we don't violate any octet rules. Right? We go through and we check our formal charges, all this kind of stuff that goes along with this. Okay? So every resonance structure has to be a valid Lewis structure. That's the third bullet point there is a little bit, I don't know, maybe a little bit too vague. So when I'm talking about the second row elements, I have a maximum of 8 electrons. I'm just trying to get you guys to think about the whole octet rule thing here. Remember, the octet rule for us is a good starting point, right? If things can obey the octet rule, that's usually what we'll end up seeing them doing. But we can certainly go beyond this, and we've seen a couple examples of this already, right? But carbon, nitrogen, oxygen, and fluorine are going to be exclusively with the octet rule, right? So if you see 5 bonds to a fluorine or 5 bonds to a carbon, you're doing something wrong, very wrong, okay? So don't do that. Only ever going to see 4 bonds to those guys at maximum, okay? All right, so the last kind of point here is how we deal with formal charges. Better structures have fewer or lower, right? So let's say lower formal charges. And what we mean is we want to get closer to 0, right? If we have the choice between making a formal charge of -2 versus -1, right? The lower the charge, the better, right? The closer to 0, if you want to think about it like that, right? So whatever you want to put there, the closer to 0 the formal charges, the better they are. Okay? I'm not saying we always are going to have 0 formal charges. Don't go crazy and just make bonds and move electrons until you get, zeros, right? Then you're going to end up maybe over-octeting things and stuff like that. So just be careful, okay? Better structures also have fewer formal charges, and what I mean by this is, right, when you go through and assign your formal charges for your atoms in your Lewis structure, right, the less overall atoms have a formal charge, the better, okay? So if you have 3 atoms and all 3 of them have Lewis formal charges, if you can draw something where only one of them has a formal charge, that's going to be better. So what we mean there with fewer is total number of atoms with formal charges. Does that make sense? You guys with me on that one, kind of the distinction there? Like lower and fewer, I know these are kind of vague terms here, but I don't really have a nice shorter way of summarizing all that stuff. If you have to put formal charges on something, put the negative charge, right? Put the negative formal charge. So negative Fc there, the negative formal charge on the more electronegative atom. And we talked about that with a couple examples that we worked through in the slides, right? So put the negative stuff on the electronegative atoms. What's our most electronegative atom? Fluorine, right? Followed closely by oxygen, right? And then we've got a close competition there between nitrogen and chlorine, right? So if you have to put a negative charge on something, look for those 4 and see what's happening with that. What's up?
Can you tell me why highly electronegative again? Can you tell me why fluorine is highly electronegative again?
Yeah, radius. What does it mean to be electronegative?
Has to do with like when you add an electron, how much energy you get?
That's okay. So that's electron affinity.
Okay.
Right? So it's closely related, but remember there is a subtle distinction here, right? So electron affinity deals with when you just have an atom in the gas state. So we've got an atom floating around by itself. Electronegativity is kind of the same idea, except when it's in a molecule, when it's bonded to something else. So the idea is how good is an atom at attracting electrons to itself, okay? And the only way you can attract electrons is to a positive charge. So the closer you can put the electrons to the to the nucleus,
Okay.
then the more electronegative something's going to be. So the smaller the radius, the closer to the nucleus, the more electronegative something becomes.
Makes sense.
It does, right? It's almost like there's a logic behind this. Right? Maybe some kind of science or something. Right? Cool. Does that all make sense? So I could have just given you guys this slide and we could have all watched movies for the last 2 weeks, right? Wouldn't that have been great? Like, no, we want to do this, right? So there's a lot of information tucked away inside this one slide is all I really want to say with it, right? A lot of important information, okay? Especially for you, again, I know I keep pointing at this and that's because I want you guys to just understand and, in a year from now, for you guys, who does have to take OChem here? 1, 2, 3, 4, most of you guys? Okay, so misery does love company, as they say, right? So time to make friends, right? But I am just kind of drawing attention to you guys for these things that do have to go through, these people do have to go through OChem, right? We will see this stuff again, so it's always going to be good to kind of keep your notes and kind of keep up to date with these things, right? You'll see it again. In fact, the first part of OChem, I have to go back and teach you guys all of Gen Chem again, right? No, not you guys. You guys have a great teacher for Gen Chem. I'm talking about the other class, right? Those guys, right? No, I'm just kidding, okay? Anyway, so good summary slide here of the stuff that we've talked about so far. All right, so let's talk about some of the exceptions. Now, I hate to use the word exception because as soon as I say that, you guys are like, no, everything's an exception and nothing makes sense and now I've got to memorize and all this kind of stuff, right?
Yep.
Correct.
But the answer is it's not really an exception. Remember, There has to be a logic behind it, right? So here we call things an exception. And we have a beryllium compound there with two hydrogens. We've got a fluorine with a boron in the middle there. And what do we know about that, or what do we notice about that boron?
Doesn't have any lone pairs.
Doesn't have any lone pairs. It doesn't have a full octet. So it's got to be miserable, right? It's terrible, it hates life. Or does it? So I've given you guys a Lewis structure, right? Every time you draw a Lewis structure, what should you guys do? Check your Lewis structure, right? You check the octet rule, you say, there's a boron that doesn't have an octet, right? You count your electrons. Did I add or leave off? Did I miss any electrons when I was drawing that Lewis structure, right? Maybe I made a mistake. Now you guys know that's not true, right? But maybe I did, right? Always go through, maybe I just left off a lone pair there, right? But if you go through and you count it up, right, each fluorine should have 7, boron has 3, so we should have a total of 21, 24, right? We've used 24 electrons. So we don't have an octet on everything. We used all the electrons we have. I know what we forgot to do. We need to give boron that octet. So what could we do? What have we learned so far?
Double bond.
Make a double bond. So why don't you guys draw a double bond, right? Because that's what we've learned to do so far. So why don't you guys take this structure, draw a double bond in there, and see what happens, okay? So take one of your lone pairs from any of the fluorines, draw a double bond to the boron. Every day I do this. Fall for my own traps. So let's take that one pair and drop it down into a double bond there. Cool. Did we add any electrons? Nope. Did everything have an octet? Yep. Okay, good. Now we're done, right? So I must have made a mistake.
Is this resonance structure thing?
Ionize the fluorine atom.
Mm-hmm.
Ionize the fluorine atom.
I did what?
Did you ionize it?
I don't know if I ionized it, but what are you looking at?
Now it's 6 electrons instead of 7.
Yeah, you're doing your
No, now
your
fluorine
magic
has
circle.
access to 8 instead of 7.
It always had access to 8. I didn't change anything with that, right?
Right, sorry.
That's okay.
But is it the best one? I don't think it is.
What do you mean, is it the best one?
It's not the best Lewis structure, because now.
Good, how do you know?
Because the B is now negative and the F is now positive.
Got it, right? Always gotta check your formal charges, okay? If you do a thing, check a thing, all right? If you do something, check what you did. Don't just draw a double bond and say, yep, I've seen this a million times. That's how life works, okay? So if you do your formal charges on this, you'll end up with a +1 on that fluorine and a -1 on that boron. Now, is there anything inherently wrong about having formal charges on a structure? The answer is no, but remember, what do we use formal charges for? To say, hey, wait a minute, okay? There's something unusual going on. What is unusual about these formal charges?
They're not all 0.
Hmm?
They're not all 0.
That's not necessarily unusual, right?
Total.
That's kind of, our goal is to get to 0 if it's reasonable, right? So that's a good observation, but what's unusual about these? Yeah.
Like fluorine is super electronegative, and so it wants all the electrons.
And
So
right
it's
now it
negative.
has a,
Yeah.
and right now it has a positive form. Are you guys ever gonna see a positive formal charge on a fluorine?
Yeah.
Probably not, okay? Probably not. So immediately, whenever you guys see a plus on a fluorine, you should go, right? Is there something that I did wrong, or is this just one of these magic cases that we've never talked about that exist in one instance in the universe? Aha, it's gotta be that one, right? That's the only possibility. I know Dr. H, all he likes to do is trick us on everything, right? No, right? If you see a plus on a fluorine, you probably did something wrong, okay? Go and check and make sure that you didn't add or remove or do something invalid, right? And all we remember, what we did here is we drew a pi bond in there because we wanted to give boron an octet. But then we end up putting a negative charge on the boron and a positive charge on the fluorine. Got it? It's still a valid Lewis structure, but it's not a good one, okay? Or I should say it's not the best one. But if we go through and do the formal charges for this over here, what do we find out?
0.
Everything is 0, right? Does that fall into our rules for formal charges? Yeah. So does it make sense that we call this an exception, but is it really an exception? The answer is no, right? We're just following the rules of formal charges. Yeah, the boron doesn't have a complete octet. So what? Right? Remember what we said about the octet rule, right? We want to follow it, it's a good starting point, but if we're outside of carbon, nitrogen, oxygen, and fluorine, we can make some exceptions to it, right? This just happens to be the case, okay? And the exceptions just come down to understanding our formal charges again, okay? And if you do the same kind of analysis, let's say, for the beryllium compound up there, you end up at the same point, okay? Everything has a 0 formal charge. So we can say, well, that follows our rules, beryllium is happy, okay? Now, what we do see, though, is that with some of these compounds that are missing the octet, they have a certain reactivity to them, okay? So, just an example here, I think they have this one in the book even, they have this idea of Lewis acid-base reactions. Now, we don't really talk about Lewis acids and bases in here too much. We'll talk about them again, I think we talked about them in Gen Chem 2? I forget now. I know we'll talk about them in OChem, right? But I think we mentioned them just a bit in Gen Chem 2 also, right? But the idea is that boron has an open orbital, right? And as soon as we have an open orbital, it's like having a nice apartment in the penthouse right next to the beach, okay? It means that it's very attractive to the very attractive to electrons. And they're going to very quickly make a bond with that. And that's actually super important. That's a really important property. Now, if you take a look on the periodic table, right below boron is our buddy aluminum. And aluminum is one of the most important catalysts industrially, right? And it's all because it's based off of this idea here, right? Remember, if we're talking about the periodic table, right, things in the same family have similar reactivity, right? So if boron behaves like this, we expect aluminum to behave very similarly also. Okay? And it's this property that is extremely useful in the formation of plastics and all these kind of things, right? Makes the world go, so to speak, okay? But the point I want to make with this here is that when we see things violate the octet rule, we start to see some different reactivity come in, is what it is, okay? Now, here's a new Lewis structure, right? We did a thing, so what should we do? Check a thing, right? So if you guys go through and do your formal charges for that new adduct over there, the new molecule that we made. we see when we do the formal charges for our new structure there?
Boron and nitrogen, both one off.
What do you mean by one off?
Boron has 4 formal charges, so its total thing is like 4 as opposed to it's 3, and nitrogen also has.
So it has 4 around it, but it starts out with 3, right? So, okay.
And nitrogen has, so boron has a +1.
Minus 1.
Or, sorry, minus
Yep.
1, and nitrogen has a +1.
Correct, right?
Wouldn't we want that to be the other way around?
That's the question, right? You're like, hey, wait a minute, right? If we do our formal charges, okay, if we do our formal charges here, we end up with -1 on the boron and +1 on the nitrogen. And what Gabe was saying is, hang on, right? One of the things that we have to pay attention to is, if we do have to have a negative formal charge, we want it to be on the more electronegative atom, right? Is it? What's more electronegative, boron or nitrogen?
Nitrogen.
Nitrogen. So you're like, well, okay, we've got these unusual formal charges, right? What can we do about it in this case?
Change the bond?
Change what bond?
Well, there you got me. I keep going.
How do we typically move formal charges around? How do we add or remove or change or push formal charges? What types of bonds do we add or move around? Our pi bonds are double bonds, right? Do we have any double bonds here? No. Can we draw any? Not without violating any rules, right? So can we do anything about these formal charges?
No?
Nope. Right? Here's the tricky part. Does that mean that nitrogen is really feeling positive? No. Okay? So what in the world are you talking about? So remember, when we're dealing with formal charges, it's a way for us to track electrons. Okay? It's a way for us to assess a Lewis structure and say, you know, is everything kind of, I don't know, what's a good word for this? Good, right? It's not quite the word I'm looking for here, right? But is everything kind of up to standards, right? Is there anything unusual that's going on? Just because the nitrogen has a positive formal charge doesn't necessarily mean it's positive. What it does mean is that it's less negative than it usually wants to be. Ugh. That's where formal charges get tricky. Because what do we know about nitrogen? One of the properties that we know is that it's extremely electronegative, right? Does electronegativity change just because it has a positive formal charge? No, right? But does giving something a positive formal charge change how it feels? The answer is a bit, right? You guys don't seem convinced, so let me give you an example here. Let me give you something to think about. So one of these polyatomic ions, right, that we didn't memorize necessarily, but that you guys have seen quite a bit, is our buddy H3O+, right? So why don't you guys draw your Lewis structure for H3O+. Yep. Mm-hmm. That's a good question. I'll answer that in just a bit. The short answer is it doesn't really matter. But there is a rhyme, the reason why we draw things in certain ways. And we'll get into geometries here in just a little bit. sure you're using all the electrons that you have access to. Where's your formal charge? Good. Now just do your formal charges. Missing some electrons here. Good. Excellent. Judge harshly. Cool, good. I'm seeing a lot of correct answers. Don't forget to, every time you draw a Lewis structure, just get in the habit of assigning your formal charges, right? Good. There it is, you do that there. Positive charge on that oxygen. Do you think that oxygen is really feeling positive? No, it's not. What does that positive charge tell us? Hey, there's something outside the norm for oxygen, okay? There's something outside the norm for oxygen. Electronegativity of an atom isn't influenced by its formal charge. A formal charge is our contrivance, our way of looking at things, okay? It tells us in this case that there's something unusual about oxygen and it can help us to predict things like reactivity, okay? But it doesn't say that that oxygen is actually a full positive if we look at this molecule. That oxygen is still feeling negative, okay? Because of its electronegativity. Okay? That's the tricky part. Does that make sense though? So I'm just asking you guys to separate the idea of electronegativity and formal charge. That's all it comes down to. Cool. All right. So what if we have some oddball things? Like nitrogen monoxide, NO. If you go through, right? We have 11 valence electrons for there. And we have 17 valence electrons for here. These are valid Lewis structures. Okay? These are stable structures. But they are fairly reactive. Okay? Be careful not to conflate reactivity with stability, right? There is important distinctions between the two. But when we have these kind of oddball species that we have unpaired electrons, right? So unpaired electrons. It's not a lone pair, it's not a bonding pair, it's just one lone electron kind of sitting out by itself. This is what we call a free radical, right? And this is probably a term that you guys have heard before, right? Especially when you're dealing with like vitamin commercials or things like that, right? You know, they're antioxidants and free radical scavengers and, you know, this kind of terms that get thrown around, right? Radicals exist and they form pretty easily, to be honest, right? In fact, that molecule at the top there is actually in your body right now. It's a signaling compound, okay? So they do exist, they are useful, but they are unusual because they have that unpaired electron in there, okay? That electron really wants to get paired up with something. And so what it's going to do is it's going to find something else, maybe your DNA or whatever, and just grab an electron out of there, all right? And if it grabs an electron out of your DNA or something important, that's when problems happen. What's it called when something grabs an electron or takes an electron from something?
Ionic?
Let's see, what kind of reactions do we talk about that we change electrons around? And something gains and something loses, right? So if you take an electron from something, right, you're oxidizing that thing, right? Oxidation is loss. You guys with me on that one? Right, so if you take one electron away because you want to get paired up, then you're causing an oxidation to happen, right? So that's where we get this idea of antioxidants and that kind of idea, okay? But these molecules do exist, right? So when they are around, We just don't talk about them all that much just because they are kind of, let's say, rare as compared to our paired electron systems, okay? All right. Now we get to, I don't know, I guess we can call it kind of controversial or whatever. We'll call it a lie. let's just be honest about it. How can we actually expand the octet then? So let's go back for just a second and ask where does this idea of the octet even come from?
The, nihilable gases,
Okay, what about them?
they have 8 in their shell, they have 8 valence electrons.
Why?
Because then the shell is all full and you don't want to react and they're nice and calm.
Right? So if we're looking at the valence shell for noble gases, we have our s electrons, our s orbitals and our p orbitals. And what's the most we can fit into one s and 3 p's? Well, 4 orbitals and 2 each, so we get to 8. Got it? So if I want to go beyond 8, then logically I need to have access to more orbitals. Okay? And so as soon as you have access to more orbitals, like our d orbitals, then we can start to over-octet things. But you're like, wait a minute. Sulfur can violate the octet rule. Are there any d orbitals in sulfur? Well, you guys see like the let's call it the logical fallacy there at the moment, right? We know it can violate the octet rule, therefore it has to have access to d electrons. But if we take a look at its valence shell, it doesn't have access to d electrons, therefore it can't violate the octet rule.
But the D thing jumps, the number jumps from 3 to 4 when you start or from 4 to 3 when you start in with D.
Correct, but we're looking at sulfur, right?
But would that have an effect on where sulfur is?
Nope, sulfur is sulfur. There it is.
So there's definitely no D orbitals?
I didn't say that. I didn't say there's definitely no d orbitals. I'm saying there's something else going on behind the scenes. Here's the reality of things. Hydrogen has access to d orbitals. Hydrogen actually has access to f orbitals. I don't know, Dr. H, it's just 1s1. Well, remember, when we're talking about orbitals, we're just talking about regions of probability, okay? Every atom has access to all orbitals, but those orbitals are not at the same energy level. So an f orbital on a hydrogen is not at the same level as an f orbital on something like tungsten. To the point that it's practically impossible for that hydrogen to access those f orbitals. It's just never going to happen. I'm not saying they're not there mathematically, it's just we can't access them. The atom can't access them. And that's where we start to see some of these, let's call them anomalies, kind of pop in. But the closer you get, right, the bigger the atom you are, the easier it is to kind of access some of these more, let's say, exotic orbital systems, I guess. For instance, if we get to sulfur, how far away is sulfur from the d orbitals? The answer is just one row away, right? Just a couple of electrons away, basically. So it's not that far. It's not too much of a stretch for it to be able to have more than 8 electrons around it, okay? Now, if that idea is a little bit kind of out there, I understand, but just the point is, every atom has access to all those electrons potentially, those orbitals potentially. It's just practically speaking, that's not going to happen unless we get to our bigger atom systems, okay? There's something else that's going on behind the scenes too. We'll talk about that in just a little bit, right? So this is a perfect example of a being able to violate the octet rule. We got our buddy chlorine, right? If you take a look at chlorine, it doesn't have access to d electrons, at least the way we see it, right? But we know that the bigger the atom, the closer it is in energy to be able to use those d electrons. And so we can come up with the Lewis structure that's there. Okay? Remember, if I kind of lost you guys here, carbon, nitrogen, oxygen, and fluorine, exclusively octet. Everything else, use your formal charge, right? So I drew a Lewis structure for you guys. How do we know that it's correct? We check our total number of electrons, right? We see that we use the correct amount. We didn't over-octet our fluorine because that one we have to pay attention to, right? That's never going to be over-octeted. How many electrons does chlorine have access to total? 10, right? 3 bonds, so 6 from the 3 bonds, and then 2 sets of lone pairs, right? So total of 10. What's the formal charge on chlorine, though? The formal charge.
No, it has a 0 negative, the formal charge.
Oh.
0, right? Formal charge is 0. What's its oxidation state? Ooh. Dr. H. That's from a different chapter. You don't understand.
Just give me 5 minutes to shift my brain into a different gear.
How'd you get +3?
Because chlorine has a -1. and
Correct.
Chlorine is less than fluorine, so
Yep.
it's the natural.
Remember, our oxidation states are those rules that we have to know also, right? Fluorine's always going to have a -1. So how could I say that the oxidation state is +3, but the formal charge is 0? What does that mean? We're looking at different aspects of this, right? So we've learned ionic charges, we've learned formal charges, we've learned oxidation states. All of those have a different applicability to it. Got it? Your job is to do what? Just know it all. It's easy, right? Geez, what have you guys been doing all semester, huh? I know it's tricky, I'm getting it. I'm just, hopefully, well, keep my humor at an 8 a.m. level, right? Right? But don't forget about your formal charges and your oxidation states and those kind of things. Those are still extremely important. Okay, extremely important. But does it make sense then why we can violate the octet rule? It just comes down to follow your same steps to drawing your Lewis structure, but at the end, check your formal charges. Got it? That's it. That's really all it comes down to. Don't skip the formal charges. You won't miss any of these problems. Okay? Cool. All right. So now that you guys feel somewhat confident in that, let's do something completely different.
And now for
Sort of.
something completely different.
So what we've done so far in this semester, right? Here's a good summary for everything we've done this semester. So if you guys remember way back in the day, right? We learned how to name that. We learned how to identify that that's a covalent compound, right? We could give it a name. You guys could calculate things like the empirical formula, the molecular formula. You guys could calculate the formula weight for it, right? Right?
Yes.
No, don't look at me that face. You're like, yeah, just lie to me, please, right? Boost my ego. I need it. Okay. Right? So that's the stuff that we've learned, chapters 1 through 5, right? We could talk about the enthalpy of the formation for that, right? All these kind of things, right? So chapters 1 through 5 is all to figure that out, right? Now we spent the next, 2-ish, 3-ish chapters, and now we can draw the Lewis structure of it, right? And we can go through and we can count valence electrons and assign formal charges and check to make sure it's the best Lewis structure, okay? But this isn't actually how this compound looks in reality, right? The problem that we have is we live in a 3-dimensional world, but we're do all our work on a 2-dimensional plane. Do you guys see the problem here?
Mm-hmm.
So it would make sense that molecules have to have 3-dimensional shape. Why? Because otherwise you guys would all be what? Flat 2-dimensional beings, okay? You guys see what I'm saying with this? Where does shape come from is what I'm asking. Ooh, that's a philosophy question. Go ask your philosopher professors about that kind of stuff. Why do we have shape? Get out of my class. Right?
Go ask
Physics department.
Yeah, no, they have a, go ask them how many dimensions actually exist, right?
No, thank you.
Should come up with 11 or 13, one of the two, right? So, but anyway, we have some problems then. Because if I want to draw the actual three-dimensional shape of a molecule on a piece of paper, that's going to be difficult to do, right?
Mm-hmm.
Well, not really though. If I asked you guys to draw a cube for me, what would you guys do?
A lot of shading.
Well, you would draw perspective lines, right? You would say, well, there's a square in the front, right? And then we kind of do that kind of deal there, right? And we understand that we're trying to add, dimension onto a flat piece of paper. You guys with me? Is that really a three-dimensional shape though? No, it's just me drawing some lines at an angle, right? If you guys kind of tweak your eyes away from what you might expect, it's still just a flat object. But the same reason why we can look at that and say, yes, it has 3 dimensions, we're going to use that same kind of idea to draw the 3-dimensional shape of molecules. Okay? And the way we do that is by using these wedge and dashes. So what we've been doing so far is drawing everything in a flat plane. As soon as you take things in and out of that plane, we have to either wedge or dash those bonds. Okay? So if you see 2 atoms bonded together, they've got that dashed line in between them that's going into whatever plane you're looking at. Okay? So if you're imagining the plane of the projector here, right? That hydrogen is behind the screen, and the one that's dashed is coming out towards us. Now, I know some of you guys already had lab this week, right?
Mm-hmm.
And you guys were using that modeling software, and you guys were kind of, right? This is the same idea here, right? I heard it was great software. Don't worry, I gave him a recommendation for next semester. Hopefully they get it fixed, but we'll see. Right? But the idea here is when we represent things coming in or into or out of the plane, we either wedge things or we dash it, and that's it. Got it? But what else do you notice about that structure that I drew here? What do the angles all look like here? They all look like they should be what? 90. Does it look like we have 90-degree angles here?
No.
No. Okay, so that's the other thing we have to represent. When we draw the molecular structure, right? The molecular structure. We try and draw things in a way to represent what the actual bond angles are. Okay? So when I ask you guys on the next exam or quiz or whatever it is, right, to draw the molecular structure, you have 2 tasks. To show me the geometry, right? Things that are coming into or out of the plane, and to represent as best you can the actual bond angles in between things. Got it? So what do we need to figure out next? Well, what are the geometries and what are the bond angles? Okay? So that's the next kind of set of things that we're going to go through here. Does it change anything about getting our Lewis structure? No. And in fact, this is the process that you guys are going to need to take. You draw your Lewis structure first, and then you go through and draw your molecular structure from that. Got it? So we're just adding something on the back end of the Lewis structure. So if you're on an exam and you don't know how to draw the molecular structure, draw me the Lewis structure and you'll get some partial credit for it. Got it? Because I know you're almost there. Okay? Not everyone's an artist, myself included. So some artistic liberties will be taken. Right? But the good news is, in the entirety of the universe, the entirety of the known universe, there's really only 6 what I'll say dominant geometries that exist. And out of those 6 dominant geometries, only 3 of them have actual 3-dimensional shape to them. And just understand, I'm kind of simplifying things a lot here. Okay, there's a heavy caveat to all these things here. But for our purposes, that's just fine. So we're going to talk about 6 geometries for you guys to know, and 3 of those are going to take wedges and dashes. Does that seem pretty reasonable at least? Seems pretty fascinating to me. I remember when I learned that, like everything only has 6 shapes to it. Yeah, pretty much. Okay? But, of course, there's some variations and some things like that in there also, right? And we'll talk about how and where that comes in. All right, so here's just kind of a summary of the stuff that I've been talking about with you guys here. If we just draw a straight line in between things, we assume that they are in the plane, okay? So every line that we've been drawing in our Lewis structure so far, represents something that's in the plane, okay? So wedge comes out, dash goes back in, just simple line in between things in the plane of the paper. That's all it is. Good? I should, I guess, point that out while you guys are copying out. You guys see the top point there, right? It says how to draw three, right below it says by convention, the central atom is put in the plane of the paper. So the point is this, right? How do I want to kind of share this thought with you guys here? So a couple years ago, they released that movie, Ender's Game, right? You guys watch that movie?
I've read the book.
You read the book, far better, but it's also, actually, not to get too far off topic, but there was an interview done with the author there not too long ago. He's really interesting thoughts, right? But anyway, so there's a scene in the movie where they're getting shot up into space, right? And there's a scene between the character and, between two characters, and there's a discussion that comes in about how do you orient yourself in space, right? Because there's no gravity, so everyone's just kind of floating around and doing their own thing. How do you guys orient yourself here on the planet? Well, we're all pulled in the same direction, right? So if I say for you guys to look up, right, you guys will all look up. Right? No one's going to look to the different directions here, right? But as soon as you lose that orientation of gravity there, then we kind of lose perspective. What that means here is that when you guys are trying to draw these maybe difficult shapes, okay, these difficult shapes on a flat piece of paper, orient yourself. And the easiest thing to do is if you can draw things in the plane of the paper, draw them in the plane of the paper. That's easy for us to do. You guys have been doing it all along and you guys didn't even think about it. Right? Like, oh yeah, just draw it here, blah, blah, blah. Right? There was no problem. So the more stuff you can put in the plane of the paper, the easier it is to draw these things. And I'll show you guys what I mean with that, okay? But that's kind of that idea is kind of tied up there in that first point. Orient yourself in the plane of the paper, and we assume the central atom is in the plane of the paper, okay? All right? There's, I think one of the drawings that they have in the book there, of course, this is, I don't know, it's not the best picture, it's not the only picture, it's not the easiest picture, so to speak. But what I do like about it is the way that they represent all of the wedge and the dash drawings outside of there. The stuff that you guys draw should look like one of those up there. Now for those of you guys who are paying close attention, you're like, wait a minute, Dr. H, you told me there's only 6. Now I count 9, right? I know. Don't worry, I'll explain this in just a second, okay? So if you guys need maybe this is kind of a cheat sheet to say, hey, is this one of the structures that we know should exist kind of thing, all right? So how in the world are we going to build these three-dimensional shapes? We'll use this thing called VSEPR theory, right? Valence shell electron pair repulsion. That sounds kind of fancy, but it's an idea that you guys already know. You guys ready for it? Did you guys know that electrons have a negative charge? And that if you put a negative charge next to another negative charge, what's going to happen? They're going to repel each other. I know. I was shocked too. But I can tell that you guys are made of sturdier things than I am. Because none of you guys fainted. Okay? Negatives repel negatives. And so when we put negative things, whether they're bonds or lone pairs, around an atom, they're going to repel each other. And so we put them together in a way so that we maximize the distance in between the different pairs. That's what this theory says. Spread things out, okay? It's the reason why you guys didn't all clump up in the same row when you guys came in here. Atoms behave the same way. They want to spread out. They want some space in between. Now, we're only going to be dealing with valence electrons, right? Because that's what we've been doing all along, okay? So all you're thinking of here is negatives repel negatives, okay? So that's what we're saying up there at the top, the electron pairs, and by consequence, the atoms stay as far apart from each other as possible. Now let's think about this for just a second, okay? So if we have an atom, okay, if we have three atoms that are bound together, okay? If we have three atoms that are bound together, so there's atom 1 and 2, okay? So let's say we have a purple atom that comes in, that's going to bond to our black atom. So we have a purple atom that we need to bond to our black atom. What's the furthest away point from the yellow atom? Well, directly across from it, right? 180 degrees. You guys with me on this one? So the only place I can put my purple atom when it comes in is 180 degrees. That's the maximum distance I can put in between atoms that are bound to a central atom. You guys with me? Okay. So that's the game that we have to play. How many stuff do we have to put around a central atom, and what's the maximum distance to spread everything out as much as we can? Okay? But it's that idea right there, and we'll continue to develop that. We're going to talk about two types of shape. We're going to talk about molecular shape and electron pair geometry and molecular geometry. Those two are inherently linked together. Okay? I'll give you the distinction, right? But there's two types of geometry, and we'll talk about the distinction between them. But the overall shape is governed by the bonds and the lone pairs present. Okay? Bonds and lone pairs affect the overall geometry. But you guys already knew that too. Why? Because what governs shape? Electrons. Okay? So whether they're in lone pairs or whether they are in the bonds, electrons are electrons. For the purposes of signing geometry, we're going to treat double bonds and triple bonds just as one region of electrons. Okay? So a term that I'm going to be bringing in here is how many regions are around our atom. I think the book might use the word domains for it, electron domains. So when I say domains or regions, they're the same thing here. Just places where electrons exist. Okay? This is important. Lone pairs occupy more volume than a bond does, though. Okay? And that's going to have some consequences. All right. So our Lewis structures, what we've been doing, right, predicts the number of valence electron pairs around central atoms. That's what you guys have been doing, right, drawing our skeletal structures and all that kind of stuff. Each lone pair constitutes one electron group or domain or region, okay? So every lone pair that you guys have drawn, every single bond, double bond, triple bond counts as one region around a central atom. And that's what these two kind of points at here. So if we draw the Lewis structure there, oops, I made a slight typo. Let's do that one right there, sorry. NO2, 1 minus. So if I ask you guys to draw the Lewis structure for nitrite, NO2, 1 minus, you guys would eventually come to something like this. And it's the central atom that's going to dictate what our overall geometry is. That seems logical, right? The thing in the middle is going to tell us what the geometry is. So if we look at our buddy nitrite here, each one of those green boxes represent a region. So one of the first assessments we have to do is draw our Lewis structure, see how many things are around our central atom. And if I ask you how many things are around the central atom, you guys would say 3, okay? And as soon as we assign our things, then we can start to assign our geometry. As soon as we assign our geometry, we can assign things like bond angles and wedges and dashes and all this kind of stuff with it. You guys following the train of thought here?
Yeah.
Draw a Lewis structure, count things. Okay, science, right? All right. Oh, I even misspoke earlier. I apologize for that. I don't know what I was thinking. Well, I know what I was thinking, but I'm sorry. So I told you there were 6 shapes. There's 5. So even less, right? The maximum that we have around something is 6. But anyway, we'll get to that later. So these are what I will refer to as the dominant geometries. Okay? Everything in the universe fits into one of these 5. In our universe, at least, our modified Gen Chem universe. There are things that go all the way up to 9, but we don't really care about those too much here. Okay? So in our universe, every answer that you're going to have is going to be a derivative of one of these 5. Got it? The only thing that's going to change, right? So the A in the middle, right? You guys see I have A's and I have X's. The A just represents the atom in the middle. The X's can represent either bonds or other atoms. The only distinction that's going to happen is when we swap an atom for a lone pair and how that changes our geometry. Got it? That's all that's going to happen. So left to right, we have a linear, what we call a linear geometry. We have a bond angle of 180 degrees. That all seems logical, right? If you have 3 things that you need to stick together, the maximum you can spread them out is 180 degrees. Next we have something called trigonal planar, which the name tells us that we have 3 things in a plane. Okay. Arranged in a triangle shape, so to speak, and so we have an angle of 120 degrees in between our atoms in there. We got something called a tetrahedral geometry. A tetrahedral is named like that because it forms a 4-sided polyhedron, right? A tetrahedron. And so our angles in there are 109.5. Next we have a trigonal bipyramidal. So if you imagine 2 3-sided pyramids sitting on top of each other, that's what's going on there. Kind of split bond angles there of 120 and 90. And lastly we have our buddy octahedral. So all 90-degree angles. So octahedral again has a similar name as a tetrahedral. It forms an 8-faced polyhedron. Right? It doesn't mean that there's 8 things there. Right? It's 6 things to a central atom. But if you have 6 things, you form 8 faces. I don't know why they necessarily do that, but I don't make the names, I just teach the names, right? So this axe notation here is kind of how I'm going to break this stuff down to you guys. The axe thing is just our way of saying how many things there are and distinguishing whether we have lone pairs or atoms, okay? So how many atoms we have, how many lone pairs we have. That's all it is. Got it? I think the book still uses the same method also. Sound good? No. I liked life before this. So a couple of quick caveats. If a molecule contains only single bonds, then those angles up there are correct. So when I ask you guys on a quiz or exam, give me the idealized bond angles. That's another way of saying this. In a perfect world, what would these angles be? And that's what they would be up there, okay? So is it important for you guys to know those angles? Yes. It's important for you guys to associate the angles of the geometries. Yes. Okay. These angles can change if we replace any of those x's with lone pairs. Lone pairs are going to start to push things around. Okay? And these last 3 points here are extremely important. They're going to explain how we construct different geometries than the 5 that I show up there. How we get to what we call the subservient geometries. Okay? And when we start to fill in lone pairs, they go in specific places based off of what we're talking about here. We want to minimize the repulsions. We want to minimize the big things next to each other. Okay? So when we put in lone pairs, we spread those out as far as we can. And it's based off of this idea, of these ideas here. Okay? Which ones push against each other the most? Got it? Cool. So that's it for today. I'll leave this up here for you guys if you need a finished copy of the exam.
Thank you.
We'll pick this back up on Friday. So we'll be having another quiz probably on Monday there. It's gonna be online again, that kind of thing. We'll move our way into chapters 7 and 8 for that one. And I am still grading your last quiz there, so if you see a 2 or a 4 or whatever it is, that's just what it's currently has, and we're gonna have to go in and adjust those grades as I grade it, okay? No worries.